Okay, so welcome back. This is part two in our series on debunking PC computer myths. And if you've ever been on the internet for any amount of time and visited any tech or hobbyist tech forums, you may have noticed there are many computer myths that keep getting repeated and repeated and amplified. And our goal here is to try and look at the actual facts and the data and see whether those myths have any value at all, or whether they're just misunderstandings or generalizations that may apply in very small instances, but in general they are kind of irrelevant to most people. So first one, we talked about power supplies, and we talked about the basics of power supply ratings and how your house electrical system is set up and how your computer and power supply relate to all the rest of the components on the your microwave and your refrigerator and all the other stuff in your house, and put it all in perspective and see how the rest of your house power supply works and how your computer works relative to that. And hopefully we gave some data to at least question or dispel some of the myths that are very common. And in this video we're going to take a deeper look into power supplies, and rather than just talk about hypotheticals, we're going to actually open up a power supply and look at the components inside, which is something few people actually do, and I'm kind of surprised at that. And we're going to actually see what's in there, and we're going to do the unthinkable. We're going to actually take a power supply and we're going to turn it on and apply an overload and even a short circuit to see how the power supply responds. And hopefully it will sense it immediately, sense the overload, and it will shut down the power supply, because what we want the power supply to do is, if something fails in our power supply or in our computer, we would really like the power supply to sense that and immediately shut down and disconnect the computer, so that we don't have any further damage. It de-energizes, takes away all the electricity from all the components, so whatever's happening, if there's a short circuit or a failed component, it's not sitting there burning and bubbling and starting a fire. So the goal is to see if power supplies will actually do that. Now, we mentioned in the last one that the ATX specification requires that there is some protective devices in the power supply that detect that the voltage is right, the current, and the power. So we're going to actually try that out and see if that works. Now, before we get into those hardware things, there are some expectations I want to address and some perspectives that people have. And I want to kind of shine some real-world light on those expectations, to see actually what engineers and what the real world thinks about some of their perceptions. I think there's a general belief by people, or people want to believe, that if they buy an expensive piece of equipment, it's going to last forever. And that's just not true. The truth is, all electronics will fail at some point. It's just a matter of when, right? No piece of equipment is perfect, right? Stuff corrodes, stuff fails, stuff gets old. And engineers are well aware of that, and they even have a metric to define, or to give them an idea of, for a particular component, how often is it expected that they will fail, right? And that's called the mean time between failures. How often will this component fail? And it's a general ballpark based on statistics and based on knowledge of the components in the system. And it just is a recognition that stuff is going to fail. It's just a matter of when. Now, there's a very good discussion of that. I believe this was Wikipedia. And it says, an estimated mean time between failures value of 100,000 hours, which is roughly 140 months, or what is that, 11 years, something like that, at 25°C, which is normal room temperature, and under full load, is fairly common. So it's fairly common to say that a power supply has a mean time between failure of about 10 or 11 years, right? So you can expect every 10 or 11 years a power supply will fail under normal conditions, normal full load, right? So that's interesting. It says engineers know stuff is going to fail, and it's fairly likely in 10 or 11 years your power supply, if it's new today, in 10 or 11 years, it's pretty likely it's going to be failed, right? And they say such a rating expects that under the described conditions, which is normal load conditions, 77% of the power supplies will be operating failure-free over 3 years, which means between 3 and maybe 10 years, you can expect that 70% of the power supplies will be operating fine, okay? And 23%, that's almost a quarter of all of the power supplies, are expected to fail within 3 years of operation, all right? So that's amazing. You know, that's basically saying engineers know that a quarter of the units are probably going to fail within 3 years, the first 3 years of operation. So engineers know this stuff is going to fail. It's just a matter of when. And they expect in the first few years of operation, it's more likely they will fail. And they also expect that as they get, 10 or 11 years, it's more likely they're going to fail. That's going to be the mean time between failures. This is kind of supported by what's called the Bathtub Curve. It's basically a measure of expected failure rate of components versus time. And it really says the likelihood of failure of new things is very high. And once it gets into service for a while, that likelihood becomes quite low. And as it gets really old, towards end of life, the failure rate goes back to being very high. And this curve is shaped like a bathtub. So it says, over time, new stuff is very likely to fail. Midlife stuff is unlikely to fail. And old stuff is likely to fail. Okay? So that's basically what engineers view about these electronic components, that when you get something new, there's a high likelihood that's going to fail. For, manufacturing problems, it's got a bad component because it's just a bad component. Maybe the user did something wrong in installation or whatever. But once all that stuff gets ironed out and the system is operating, it generally operates at a fairly low failure rate for a number of years. And then as it gets older, the likelihood goes up that it's going to fail. So engineers know this stuff is going to fail. It's just a matter of time. So what can you do about that? Well, number one, don't buy junk. All right? Don't think that, you're going to save money on any component, power supply or whatever. Don't do it if you will really care about, your equipment failing, right? If you don't care about it failing, then fine, buy junk. But the point is, if you buy junk, it's more likely to fail, right? And also, this is something that few people actually discuss on the internet because nobody wants to admit they did a mistake, but don't cause something to fail. Know what you're doing, right? Learn about stuff before you do it, and don't cause it to fail. I'm pretty much convinced that a large portion of the computer failures are due to user error. And by definition, since people who don't know something are going to cause it to fail, the fact that they don't know it means they don't recognize that they caused it. They'll blame somebody else. If you do something that causes your computer to fail, but you thought it was right at the time, nothing tells you that it was wrong. So why would you think it was your fault? You blame it on somebody else. So I think, that's a big thing. Make sure you know what you're doing, right? Study it first. Don't just listen to somebody on the internet. Verify, test things, and learn how to diagnose things yourself, right? And you can also realize that engineers understand that stuff will fail. And as a result, they design self-protecting features in the equipment to try to prevent those failures from damaging the rest of your system, right? They know it's going to fail, So the best they can do is put equipment in there that senses a problem, and as soon as it senses the problem, it disconnects everything so that it doesn't cause a cascading problem on your system, computer burning up or whatever. So the best you can hope for is that those features that they engineer in and are required by ATX specification are successful in protecting the rest of your system if something fails. Okay? So at least we got similar expectations and perspectives on this whole equipment thing. Now, what really is a power supply? And we're going to get closer to the hardware level and actually look at some of the major components in a typical power supply. And inside this dashed line, this box, I've put some of the major components of a typical power supply. Now, this is going to vary a lot, and it's not perfect for every particular power supply, but the general concepts are here, and it should give you at least a good idea to start off in your investigation of power supplies into the details of your power supply. Okay, so over here on the left, I have a wire coming in from the outlet that connects to the utility. And as we talked about in the previous video, the utility supplies us with 120 volts, and it's a sine wave. It's called alternating current and voltage, and it looks like this, right? It goes high, and then to zero, then negative, then to zero. That's how it comes out of the utility. Now, the first thing, when you go into a power supply, usually the first thing that it is connected to is called a fuse. And the one we're going to look at has a 10 amp fuse. Now, what is a fuse? We talked in the previous video about a circuit breaker. A circuit breaker is a mechanical device that senses the current flow through the wires, which is our analogy in the previous video was of water flowing through a hose. With electricity, it's electrons flowing through a wire, invisible electrons. So the circuit breaker senses on your house circuit breaker that applies to circuits in your house, it senses, for example, if the current flowing exceeds 15 amps, then engineers say, well, if it's above 15 amps, something's bad is happening. So this circuit breaker is going to immediately sense that and open up the circuit to disconnect everything in your computer and your motherboard from the electricity, so whatever's happening stops right away. A fuse is just like that, but it's not a mechanical, it doesn't have a mechanism in it. It's basically just a continuous wire, but the wire inside the fuse is a very thin wire. And it's designed, in this case, so if 10 amps or more is flowing through this wire, actually more than 10 amps is flowing through this wire, that thin wire will heat up and melt. And it will do it very fast. And by melting, it will open up this circuit, and doing the same as a circuit breaker, it opens up the circuit and it disconnects the electricity from your power supply and motherboard. So it protects, it senses overcurrent and protects your system. So if something bad is happening downstream, it will disconnect it so that whatever's bad is happening will stop. And then you can find the problem, repair it, and then put in a new fuse and turn on the power supply and you're all set. Okay? So the very first thing is a protective element. So don't think that, a power supply has nothing and if something happens, it's going to blow up. No, it's got a 10 amp fuse, and we're going to see it's got other stuff. So the next thing it encounters is a rectifier, and we said we have a alternating current and voltage. We need to somehow make that look like a DC direct constant value of voltage and current. So we do that. We start out with a rectifier, and a rectifier basically takes this wave and flips this part of the wave so that all of them are like this, okay? That's rectification. It just takes the sine wave and makes it look a little bit more like flat DC in one direction. Then, to make it even more look like DC, it goes through a filter. And the filter output looks like this. and it's got what's called a little bit of ripple, but it's a lot closer to DC. Okay, so now you've got direct current. It's still at a high voltage, but it's flat. And if you applied that high voltage to your motherboard and your chips, they would burn up and they'd be destroyed. So your chips and your GPU and your microprocessors need to have low voltage, DC low voltage. So there's another stage here that takes this and converts it down to 3 volts or 5 volts or 12 volts. Okay? Once that's done, it sends it to the motherboard, and that will power the equipment on the motherboard. Okay? Now, there's one more component, and this is one of the more important for the point we're trying to discuss here, and that is called a supervisor. All right? It's a circuit that measures your 3 volts and 5 volts and 12 volts going out to the motherboard, and it checks continuously, kind of like the fuse does. It checks continuously if the voltage is okay. Is it within the limits? Is the current going to the motherboard okay? Is it within limits? Is the power okay? Is it within limits? It senses that continuously, and if there's a problem, the logic inside this supervisor will say, hey, wait a minute, something's bad. I don't know if the power supply has a problem, but the voltage is low, or the current is high, or something's going on. I'm going to send a signal back into the power supply and shut it off. And it does that by shutting off probably the rectifier, and that basically shuts off all the electricity to the power supply and the motherboard, thereby protecting whatever's going on. It will stop, right? It won't be melting components anymore. It will stop, right? So now you've got two protective devices, and the supervisor actually does at least 3 things, measures 3 things to make sure everything's okay. So there's a lot of protective stuff going on here to make sure that things don't blow up, that as soon as a problem is identified, the power is shut off, so that nothing, any problems don't continue. All right? Now, what are we going to do? I said we are going to apply a short circuit to the power supply and watch the response of the power supply. Okay? Now, I've got a power supply. It's a 460 watt power supply. And it's all by itself. There's no computer. It's just a power supply. I plug into the wall, and it's got these. This is the motherboard power connector that plugs into the motherboard to power the 12 volts and the 5 volts and the 3 volts. So it's basically just the power supply and the connectors. All right. So what I want to do is, with just that configuration, I want to apply an overload and a short circuit to the power supply and measure the response of the power supply, right? Does it shut off or doesn't it? And if it shuts off, if I clear the problem, will it reset and start up like nothing happened, all right? So how am I going to do that? Well, here is, like I said, the connector that you plug into the motherboard from the power supply, and it supplies the 3, 5, and 12 volts to the different components on the motherboard. 12 volts like for the GPU, and 3 volts for some of the integrated circuits, and you can look at the list of which components take which voltage. But anyway, the first thing we have to do, since this power supply is not connected to a computer, it doesn't have the benefit of the on-off switch on the computer. And this power supply requires an external on-off switch. So what we can do is, you can see I've got this paper clip plugged into these 2 plugs on this connector. And it turns out the green is the power supply on switch and black is ground. So the switch on your computer, when you press the power, you turn the computer on, it sends a signal to this green signal, and it basically shorts these and turns on the power supply. All right. So what we're going to do is, since we don't have that switch, we're just going to run a jumper to connect these two. All right? So this is our on switch. We're just running the jumper. Now, the next thing we're going to do is we're going to apply the overload and the short circuit. How are we going to do that? Well, we're going to apply it to the 12 volt, what they call the rail. There's a 12 volt rail and a 3 volt rail and a 5 volt rail. It's basically separate circuits. So we're going to connect the 12 volt pin, which is this one right here. There's a couple of them. We're going to connect that through a variable load, and we're going to vary that load so that we go to the rating of that 12 volt and we go beyond and overload it and do a short circuit to see how the computer responds. So we're going to manually adjust this thing until we get to a big overload and see what the computer does. And of course we have to connect it to grounds, so the 12 volt goes through to ground, and it acts like a load current. Now, this 12 volt rail is rated at something like 18 amps. All right? It could be 10 or 18, something like that. It depends. I'm not sure about this exact rating, but it's somewhere around 10 or 18 amps. So let's say it's 12 amps. If I have 12 volts and I want 12 amps to flow, which is rated load, this would have to be 1 ohm, right? So 12 over 12 equals 1 ohm. If it's 18 amps, this has to be less than 1 ohm. It's got to be like 0.7 ohms. And that will cause 18 amps to flow. And if I want more than 18 amps, if I want to overload it, I've got to get less than 0.7 ohms. So I got to be down near 0 to 1 ohm. And we're going to use a 0 to 5 ohm, what's called a rheostat. And it's basically a variable resistor that is going to simulate a load that is overloading our 12 volts. Okay? So at some point, when we get down probably lower than 1 ohm on this rheostat, we're going to draw 10 or 12 or 15 or 18 amps, and that's going to overload this 12 volt rail, and hopefully the supervisor is going to say, wait a minute, I've got an overload here, I'm going to shut down, and it's going to shut down the power supply. All right? So how do we know if the power supply is shut down? Because we don't have a computer. Well, we talked about the ATX specification in the previous video. One of the requirements of the ATX specification is this power good signal, all right? And it's the gray wire on this connector, and you can see it right here, I think. And it's this pin number 8, 9, 10, 11, 12, whatever, 8, 7 or 8. And if the power is good, so basically it's sensing this power going to the motherboard, and if everything's fine, and these are all within specification, it will send a plus 5 volts DC to this power good signal. And we can measure that with a voltmeter between power good and ground, and we can see if this says 5 volts, my power's good, the power's on, and everything's okay. If this goes to 0, our voltmeter will show 0 volts, and that means the power's off. It shut off the power because there's a problem. Okay? So another good thing about ATX specification, it requires that there's a signal coming out of the supervisor that says, okay, all is well. So it's really useful for us and for, knowing that when things are good and when things are bad. So we're going to have this configuration, and we're going to check as we bring this down and overload the circuit and maybe even get to a short circuit. We're going to see, does the power good go to 0, which means it shut off the power supply. And then, if that happens and it shuts off, we're going to disconnect this overload to get back to normal condition. And when everything resets, we're going to try and turn on the power supply again and see if it powers up like nothing happened. Okay? So that's the way we're going to actually learn, at what point does this shut off when bad things happen, because we can see at what point was the rheostat, what was the resistance, and we can calculate how many amps it took to shut this off. And there, by doing that, we can say, okay, so it really, really does work. Instead of having to listen to people on the internet who don't really know and just take their word for it and not really get our hands involved in actual hardware. So the next thing we're going to do is actually go and do that. Okay, we're going to start out, and you can see I've got the power supply cover off. And here is the power supply, and I've got a multimeter that'll help us read the status of the power supply, and some probes connected to the main motherboard power connector coming out of the power supply. And if we look in the power supply, right here we've got the main power coming from the wall outlet, and you can see it comes in and goes through this choke, which we'll talk about later. But the first thing it sees, the first thing it connects to, is this device right here. And that is called a fuse. Okay, this cylindrical thing right here. It's the first thing that connects to the wall outlet as it comes into your power supply. And this, if you can see here, it's a 10 amp rated fuse. So this is one of the protective devices we talked about that senses if the current exceeds 10 amps in this case. Inside this cylinder, there's a very thin wire that will melt, and it will open up the circuit, and this entire power supply will be disconnected from the wall outlet as well as the entire computer. So it will protect anything downstream in the power supply and the computer if it sees an overcurrent. Now, if you look over here on this circuit board, you can see there is this chip here, which is an integrated circuit, and it's got, I think, 16 pins, and that is the supervisor, the power supply supervisor, which has the logic that checks to see if we have good voltage, good current, good power, and if anything happens and it goes outside the allowable range, the logic inside this chip will go through and it will send a signal to the rest of this power supply where it's doing the rectification, and it will shut it off. So that shuts off the power to the power supply and to the computer. So you can see those things we were talking about actually exist. So the next thing we're going to do is, you can see here I've got some connections like we discussed to the main motherboard power connector. Okay, I've got this jumper which simulates the closing of the power switch on the front of the computer. It's basically the switch you turn the computer on with. And this red and black probes are connected to sense when the signal for good power comes up. And again, that's a 5-volt DC signal. So whenever these two probes measure 5 volts on this meter, when this says 5 volts, we know that we've got good power and everything is within the correct range. The voltage is correct, the current's correct, and it sends that signal to the motherboard and says, okay, we're ready to go and you guys can power up. Okay, so I'm all set to go, and what I'm going to do is I'm going to I'm going to plug the power supply into the wall outlet, and there it is. It just turned on. You can see the fan powers up, and you can see now this reads 5 volts, 4.95 volts. So that means the power's good, everything's ready to go, the fan's going, and it's sending the power to the motherboard via this power connector. Okay, so what we're going to do next is we are going to overload this power supply, and we're going to connect to a couple pins here in the connector, and we're going to simulate overloading the power supply so that we get to the point where it shuts off, and we're going to determine if that's damaging or if it just resets, and then we can turn it back on later. Okay, so before we jump in to start overloading our power supply, It's important that we look at some of the specs of the actual power supply to get a feel for what to expect. You know, at what point are we going to overload and how do we know that? And maybe get a little more information about the supervisor circuit to see exactly what does it actually do and what should we expect from it and how does it do its thing. So this is the nameplate from the power supply. You can see it's a Dell switching power supply. Manufacturer Delta Electronics actually made it. And maximum power is 460 watts. And you can see down here, it lists all of the outputs it provides. And you can see it provides 1, 2, 3, 4, 5 outputs. And those are called rails. And basically, it's separate circuits coming off the power supply to power different things. So we've got 1, 2, 3, 12 volt rails. And we've got a 5 volt and a 3.3 volt rail. And these are the ampere ratings of each of those rails. We're going to be dealing with one of these 12 volt rails. And you can see we can expect, as we mentioned before, like 16 or 18 amp rating for these rails. Okay, so we want to have a rheostat that can get us to about 16 or 18 amps on that single wire rail. And the fact that it's a single wire is going to come up in a bit. It's important. So basically, this is how we came up with the knowledge of what that wire, what that 12 volt wire is going to be rated for. Something like 16 to 18 amps. Okay. Now, what I did is I did a little searching on some supervisor circuits to try and get a schematic to get a little bit better feel for exactly what does this thing do. And I think the one I've got in this power supply is kind of outdated and been replaced by another version, but I found one that looks very similar, and I think it's pretty much gives you a good idea about exactly what type of functionality it has. This right here is the integrated circuit we looked at in the other part of the video. It's got 18 pins, and you can see it's got plus 5 volts out, 3.3 out, and then 3 12 volt out. So that's not really very common to have all of those outputs, but this one does, and it's got the same pins. So I think it's probably similar functionality. So now, since it's got 5 rails or 5 circuits, this guy has to measure voltage and current for each of those rails. So that's 2 things for each rail, and there's 5 rails, so that's 10 things it has to measure. And these 5 right here are the voltages going out of the power supply to the motherboard. And these are the currents going out of the power supply to the motherboard. So you can see all of these wires are just sensing the output of the power supply and going into this supervisor circuit. So 10 out of 18 of these pins are just inputs from the power supply output. Now the outputs, there's only 2 real outputs here. This number 18 is power good, and we talked about that before. That's the 5 volt power good output that says all is well. All of these currents and voltages are fine, so I'm going to say, okay, you're good. We can go ahead. The other one that's important is this fault protection output, number 3, FPO. And FPO is the one that says, if any of these are bad, if they're not within their design specification, this says, uh-oh, shut it all down, and it sends a signal out here to shut down the power supply. So these are the big guys that do the main functionality of the supervisor. There's also a reference input where you adjust the fault protection settings. What value above the rating do you want to start to call it a problem or a fault? But basically, that's what it does. It takes all these inputs, does a little logic, and says either you're good or you're bad. Okay? Now, what I've done briefly is to try and get a feel for, with our rheostat, which is going from 0 to 5 ohms, and I've got that plotted here down on the bottom. Here's 5 ohms, 4, 3, 2, 1, and then less than 1. I've plotted when we've got the rheostat at those values, what current and what amps and watts are going to be drawn by the power supply, so we can figure out at what point are we overloaded, right? So, for example, at 5 ohms, which is the maximum of the rheostat, you've got only, I don't know, 30 watts. So you're down here on the watts, and then you've got, I don't know, 3 amps or something like that. And then as we cut down the resistance, we crank up the load. When we're down at 1 ohm, now we're starting to get into the overload area of the 12 volt circuit. And that is, remember we said it's about 16 or 18 amps? That's right here. So right around here, around 1 ohm or less, we're starting to get into the overload part of the power supply. Now, there's one more bit of information that's very useful here, and that is the ATX specification we talked about before says no single wire of your power supply can run at more than 240 watts, okay? Because they're concerned things will get damaged above that. So it says above 240 watts on our 12 volt wire. If it gets above that, that supervisor better shut down right away, because that's a requirement from the ATX. So we're right here is when we're getting into, you can see 200, a little over 200. So we're expecting in this range, we're going to probably, if everything's working and the supervisor is actually there and doing its thing, somewhere in this range of 1 to 0.5 ohms on the rheostat, this guy should shut down, okay? Now, this rheostat we've got, you'll see is a big old monster thing, and it's not real accurate. And we're getting down in some very small ranges, so I'm guessing somewhere around 1 or 0.5 ohms, this thing should shut off. So we'll see. And the other thing is, once it shuts off and we disconnect the load, can we start it up again? Okay? Okay, so I've modified my setup a little bit here in order to do the overload and also to provide a little bit more monitoring information about the power supply as we overload it to see exactly what happens. Now, I mentioned before I've got the meter over here, and this is monitoring the power good signal from the supervisor. If everything's good, I'll see 5 volts. Here I've added a watt meter, which basically measures the entire power usage of this entire power supply measured at the wall. So it measures how much we're drawing from the power company. Okay. Right now with the power supply on with no load, it's basically just 8 watts. Right. Down here you can see the fan spinning. And that takes 12 volts, so we know the 12 volts is good. We know the power is good, 12 volts is good. And right here you can see an LED that I've connected to the 3 volt supply. So we also, when the light is on, we know that there's 3 volts, okay? So we've got a bunch of information that tells us that things are going well, or not. When the power shuts off, we should lose all this, the fan should shut off, light goes off, power goes to 0, and this goes to 0. Now this right here is the big player. This is called a rheostat. It's a variable resistor, and its job is going to be to apply resistance between 0 and 5 ohms across the 12 volt circuit. And as it gets from 5 down to 0, we're going to be overloading it. And you can see I've marked here the ohm values. So it starts out with 5, 4, 3, 2, 1, and 0.6 down here. So when it's down in this range, we're expecting that the power supply will be overloaded, and we're hoping that this supervisor circuit will automatically shut off the power supply and allow us to disconnect. You can see I've got this switch, an on-off switch, that just connects this rheostat across the 12 volts. Okay, so now we're ready to overload our power supply and apply a short circuit ultimately. Now you can see the power is on, there's no load connected, the rheostat is not connected, but I've got 8 watts being drawn from the wall. I've got the power good, I've got the yellow light for the 3 volts, and you can see the fan is spinning. So what I'm going to do is I am going to connect the load and start out at the maximum resistance, which is the minimum load, and that's going to be at 5 ohms. So I'm turning on the power, and you can see we're measuring 43 watts from the wall, okay? Power's still good, lights are on, fan's spinning. So now I'm going to crank it down to 4 ohms. And you can see we're about 50 watts drawn from the wall. Everything else is good. Down to 3 ohms. And we're up to 60 watts coming from the wall. And now we're down to 2 ohms. And we're 80 watts, everything's fine. Now when we get down near 1 ohm, we're expecting this thing to shut off. So I'm turning it down, 1 ohm, 100 watts. And there it goes. It's shut down. You see the fan's off, 0 volts, 0 watts, and very little voltage on the power good. So it worked. It shut down around rated load. So I'm going to shut off the power from the wall. And now what we're going to do is I'm going to turn this back to minimum load. And what we're going to do is see if if I disconnect the load, which I'm doing now, I'm turning off the switch, and that should disconnect the load. And we should be able to, hopefully, turn the power from the wall back on, and the power supply will work fine and allow us to start up, kind of simulating, we found the bad component, and we'll see if we can just restart the computer and go on with our business. Okay, so the load's disconnected, and I'm going to go to the wall outlet and turn on the power, and there the power's on. Wow, we're back to normal. So you can see we've got 5 volts power good, we've got the 3 volts on, we've got the fan spinning, and we're drawing 8 watts again. So the point being that the power supply supervisor works as expected, okay? And it's designed to prevent bad stuff happening to your power supply or your computer if you get a failed component. So, the myth about power supplies blowing up and causing problems, probably not really based on much fact. So hopefully now you understand some of the design of the power supplies and how engineers make sure as much as possible that bad stuff doesn't cause big problems. Okay, so again, do not do this at home. This can be extremely dangerous. You can get hurt, you can get killed. So do not do this at home, especially if you found yourself during the series saying, I wish you would get to the overload part quick. You have to think these things out. You have to know what you're doing. You have to, it's why we spend time looking at the ratings to see what we're up against. So do not do this at home, okay? I also, when I did the video of the overload, I didn't quite show when it got down to the overload what the watts drawn from the wall outlet was, because I cut off the meter, but I did it again. It's basically around 130, 150 watts, but keep in mind these are very low values of ohms, and this rheostat is not a very accurate device. It's not designed to be accurate, so it could be off by half an ohm or something, and you wouldn't know it. So I'm taking that with a little bit of grain of salt. But the point is that it actually shut off quicker and sooner than I thought it would. So either the rating wasn't as high as we thought, but that's somewhat irrelevant to the point that this supervisor circuit really works well, really works fast, and is very sensitive to an overload. So again, it further supports that these things are designed so that your power supply and your computer don't get damaged, okay? So I hope these two videos have given you some good information about power supplies. The goal is for you to take this and springboard into your own learning about computers and power supplies and other equipment. So again, hope it helps. Take care and have a really good day. Thanks.